The New Quantum Era,
a podcast
by Sebastian Hassinger
and Kevin Roney.
Hello and welcome, listeners, to a special episode of the podcast. It's just me, Sebastian. Kevin is unavailable this week, and we've been trying to keep to a more regular bi-weekly schedule, so we agreed that I should just go ahead. I was in Paris last week for Q2B 2024. It was the second year of the conference. It's an international expansion of Q2B Silicon Valley, which QCware began in 2017 as an attempt to explain quantum technologies and their progress to enterprise customers. At the 2017 conference, John Preskill actually gave the keynote, and that's where he coined the term NISQ, or Noisy Intermediate Scale Quantum Computers. Q2B Silicon Valley in 2023, this past November, was actually when the Misha Lukin Vuletic Logical Qubits paper was published. Of course, we talked to Vuletic a couple episodes ago. That was a great episode. This conference really continued to demonstrate increasing levels of sophistication, I would say, in the techniques and the technology itself. There are quite a few really interesting talks that combined sort of state-of-the-art classical approaches to simulation with forward-looking quantum approaches that are anticipating, these logical qubits and more capable devices that will be able to be combined eventually in production deployments. So there's a real sense of sort of preparing for the post-NISQ era that we're starting on now. One researcher who presented some truly interesting work along these lines in material science was Houlong Zhuang from Arizona State University. So at one point after a break, I grabbed him and took him into a private room that was very kindly provided by QCware. Thank you, Sandrine. I owe you one. So what follows is our conversation. Please forgive the room tone. I was just recording on my laptop, but I think it's fairly listenable, so please enjoy. Okay, we're here at Q2B Paris 2024, second year of the conference. It's put on by QCware. It's a great event. We've been having a bunch of fantastic talks, and it's really great to see everybody here and sort of hear what's going on in the industry. And I caught a talk yesterday that was really interesting by Houlong Zhao, who's here with me now. He's from Arizona State University. And Houlong, thank you for joining me for the conversation. How did you get started in quantum computing? What's sort of your path to getting here?
So let me introduce myself
first. Please. Yeah.
So my name is Houlong Zhuang. I'm an assistant professor from Arizona State University. So how did I get into quantum computing? I started as when I first joined ASU, I started teaching a very basic mathematics class. I told you yesterday is linear algebra.
Right.
And my initial purpose of teaching that class was I was very interested in machine learning.
Right.
And machine learning basically is applied linear algebra.
Right.
So I had a chance to teach that class.
Right.
And then after I taught that class, I realized, linear algebra can be applied to so many different...
It's kind of like the native language of qubits, right? I mean, that's kind of instead of Boolean algebra, you're actually using linear algebra when you're doing a quantum algorithm.
Exactly. So, for example, all the gates, people call gates in quantum computing, but essentially they are unitary matrices in linear algebra.
Right.
So if you know linear algebra very well, then it's automatically you can.
It's a linear algebra machine.
Yeah, and then I was trained in density functional theory, computational material science.
Right.
Basically, you apply linear algebra again.
Right.
To solve this eigenvalue problem.
Right.
When you solve this eigenvalue problem, you know the eigenvalues, and eigenvalues can be interpreted as the energy levels of electrons.
Right.
Then even you don't do the experiment, then you can predict the properties of materials.
Right.
Yeah.
When did the DFT sort of approach to material science? When was that invented? Or discovered, I guess. Science.
It was. It dates back to 1960s. The original paper, if I remember correctly, they were published in 1960s. And one of the inventors, so he received Nobel Prize in chemistry in 1980s.
Right.
Yeah, and this is a very very efficient way to solve these quantum Schrodinger equations.
But it is like it can be very difficult computationally, though, right? Like on a classical computer, a DFT problem can very easily outscale the size of the computer you have, which is why quantum computing is sort of interesting for material science.
Yeah, it depends on like the level of theory you apply, because standard DFT. So one of the most challenging part we call is strange correlation function. Essentially, it's how electrons interact with each other, right? They interact each other in two ways. One is the classical way. So by classical way, I mean, you are negative charge. I'm also negative charge. So we apply Coulomb's law. Right? That's the classical. But the quantum part of interaction is very complicated. We don't know exactly what's going on. So that's why we use another approximation even in DFT, in practical DFT. In principle, DFT is accurate theory, which means that if you know the interaction, you can solve it accurately. But we don't know the interaction, so we need to apply some approximation to approximate these interactions. And we know that this approximation can be applied to certain systems, but for some complicated system, we call it strong correlation system, and this kind of approximation does not work. So then you keep on adding more and more approximation, so it starts to deviate from the original.
It's similar to the problem in chemistry, like computational chemistry. You're building approximation on top of approximation. Eventually, your accuracy, your results are just not accurate enough to be useful. So it's similar with material science.
So
and if you have an accurate DFT calculation, what does that tell you about what does that predict about the material's characteristics?
Oh, that's a very good question. So essentially, all you need for an input to classical computer simulation is the atomic arrangement, right? So you can, for example, input the atomic arrangement on carbon atoms in the way of diamond, right? And you can also input the arrangement of carbon atoms in the way of graphite, right? And then you can input those two structures to DLT program, and DLT program will give you two energies.
I see.
And then it will tell you which energy is no energy. So in principle, no energy means more stable structure.
Okay.
Yeah. So which means that you can input the arbitrary combination of atoms or species. It will give you some energy.
And from that energy, you can derive sort of the characteristics. Like diamond is a very hard substance, and graphite is softer. Like that can be derived from from those energy values.
Yeah, actually, so there are several mainstream DFT programs for the solid state communities. For example, Quantum Espresso, VASP. So or Casta from Cambridge.
Okay.
Actually, all those programs, they are called total energy based methods. Which go back to your question. So everything or many properties can be derived from total
energy. That's cool.
So for example, elastic constants can be written in terms of some derivatives of total energy.
Wow, that's cool. That's really cool. So, okay, so that's a foundation on DFT and material science. So you're now looking at a way of using quantum computers to solve certain aspects of or challenges around DFT, right?
Yes.
And how are you doing that?
So
we're hoping to do that.
Exactly. I mentioned earlier the most difficult part is the quantum interaction between electron and electron. We call it strong correlation.
Right.
But many material systems, especially when one molecule chemically interact with some substrate material, there's some charge transfer.
Right.
And you cannot use the standard version of this functional to describe these interactions.
Okay.
So in that sense, you need to use this very complicated many-body theory.
So what's an example of that type of molecule interacting with the substrate? What is that, like a composite material, or with the layers? Is that sort of thing?
Oh, many examples. Okay. So for example, if carbon dioxide molecule is chemically at the source of some ionic liquid.
Okay.
Yeah, as far as they start to have some charge transfer, your electron become mine, my electron become yours.
I see.
Right?
I see.
So electron interactions start to be very complicated.
Right. Okay.
Yes.
Interesting. So it's broadly applicable. You have to do the quantum calculation, which is quite complicated. So you're looking for a computationally efficient way to do that on quantum computers.
Yeah, and then you can do very complicated quantum chemistry by adding more and more many-body. We call it many-body facts.
Right.
And quantum computers, they are promising to help solve this, to implement this, for example, CCSD, this couple cluster method.
Okay.
Yeah.
Interesting. So what is unique about your approach then? What's your research focused on?
Oh, so my talk yesterday was about a system called a high entropy material. So it's different from conventional alloy. So conventional alloy like in the steel, which makes the chair you are sitting on. Yeah. So,
I'm familiar with steel.
Its dominant element is iron, maybe 90% iron.
I see.
And there's some tiny amount of carbon.
I see. Okay.
Less than 0.3% of carbon. We call it conventional alloy.
Okay.
One dominant alloy.
Right. Okay.
And then very small amount of elements.
Got it.
And in contrast to this conventional alloy, we have this high entropy alloy. So which means that you have many, many elements. So the original experiment doing this high entropy material system is one undergraduate student from UK university. So he was doing some undergraduate thesis. So his advisor asked him to mix more than 20 elements together. Just mix together to see what you can get out of that.
It reminds me of, sort of being a kid and like mixing stuff in the kitchen to make like a magic potion, just throwing a bunch of spices in and seeing what happens.
Exactly.
Right?
Like the mall is different, right? Yeah. Just like you go to some buffet, you eat so many varieties and you mix together. Maybe.
Right. Make a new food.
Yeah. Or maybe you can make your stomach upset.
Okay, so what did he get when he mixed together the 20 elements?
The original article actually not much, like innovative.
Soup.
Yeah, it just very, a soup, exactly. Just a new way. But after maybe in the same year, a Taiwanese group, they independently did similar experiment, mix different elements together. Yeah, and then from then on, more and more people start to explore this so-called computational space. Right? You can imagine each element is one axis in a high-dimensional space.
Right. Which starts to sound like the Hilbert space.
Exactly. Yeah. It's Hilbert space. Exactly.
As soon as you start saying high dimensionality, I think of qubits all in entanglement.
Yeah. So you can imagine hydrogen is x-axis and helium is y-axis. Right. In the same group of elements, they may not necessarily have orthogonal axes, but they may be close.
Right.
Yeah.
Very complicated.
Yeah. And then now this high entropy material, this family of material become very popular in the material science community. You can find almost high entropy of everything. High entropy superconductor, high entropy semiconductor, high entropy catalyst.
Interesting.
Yeah.
And why is it becoming so popular? Because there's so much that's unknown to be discovered about it. Is that?
Yeah. You can imagine this, each element is, it's a pixel, right?
Okay.
Yeah, and then you can try to paint some new material.
Cool.
Using mixture of
That's really cool.
pixels.
But I mean, it sounds like, you said yesterday in the talk that there's a combinatorial problem, right? You got N by N or M by N or whatever. There's like multi kind of combinations just to start with. So is that you're starting with trying to narrow down the possibilities that are for your sort of research space or your experimental space? Is that right?
Yes.
Yeah.
So we originally start from classical machine learning. So we have some training data set from experiment saying, which combination of elements can give you some certain properties.
Right.
And then we can train the deep learning model.
Right.
And then so that next time you have a new mixture of elements,
right.
I can predict
for
you the new property.
Yeah.
Yeah. And we started kind of very early. So I had a very good master student working with me. So we published one of the very earliest article using this deep learning for discovering high entropy alloys. And it was published in 2019. Now it has been cited over 300 times.
Wow.
Yeah.
That's pretty good for 4 years.
Exactly.
That's great.
Yeah.
That's great. So that was the classical machine learning. Was the next step to start adding in quantum simulation, or were you applying quantum to potentially get a better machine learning model?
Yeah, we have already started the quantum machine learning model, trying to achieve the same accuracy using available quantum simulator and quantum hardware. Actually, yesterday I presented some results.
Right.
But we used a very rudimentary encoding of the high entropy alloy data. So we only use the chemical formulas.
I see.
Yeah, but I think we can do a better job. For example, give some more input or some more chemical intuition. Yeah. So in our work, we haven't considered the relation if some element in the same group, right? They shouldn't be orthogonal to each other, right? But in the work we are now, we assume it's orthogonal to each other.
So better sort of starting assumptions.
Or different ways of encoding this.
Interesting.
Yeah.
Is that challenging, by the way, with quantum machine learning? I mean, the preparation, the state preparation is often really a lot of the overhead, right? Because you have to fit that high dimensionality into a very small number of qubits. Is that sort of part of the challenge?
Yeah, it's part of the challenge. But I think another challenge comes from the noise of the qubits.
Of course.
Right? And each material must be able to be written in terms of its composition or chemical formula. Right? But we have about 100 elements, which means that if we do 2 to the power of 7, it can cover all the elements in the field.
2 to the power of 7 qubits, or?
Yeah, 7 qubits.
Oh, 7, wow.
Yeah, 7 qubits. Wow. Because you can use one string of 0 to 1 to represent one.
It's all vectors.
You can consider the relation between elements.
Right?
Yeah, all linear algebra, exactly.
Right.
Yeah.
That's so, I mean, I find that so fascinating. I think coming from a classical computing background, that's the hardest thing to sort of wrap your head around is thinking in vectors, thinking in encoded vectors. And of course, as you said, that's happening in classical in the area of machine learning, with linear algebra. But it's still like algorithmically, that feels like the biggest barrier to entry for people with a classical background is to start thinking in that matrix multiplication kind of space.
Yes.
Right. I mean, like Peter Shor's big, sort of breakthrough is having that incredible, quantum phase estimation kind of black box for the the factorization happens almost magically, it seems, because of the way you approached it. It's such a cool part of the whole theory.
Yeah, I taught a class and I assigned Peter Shor's algorithm as one of the homework problems. And one student in my class, so he did the exercise. So he decomposed 15 into 3 and 5. And he solved the problem. And he wrote me an email saying that he felt very powerful after solving that problem.
Sure.
That's the first this kind of comment I received from students.
That's cool. Yeah. That's also, by the way, that's IBM research in 2001, I think. That was the first successful use of Shor's algorithm on 7 qubits on an NMR device. And they factored 15 to 3 and 5.
Into 3 and 5, yeah.
Which doesn't sound like that impressive a task, but until you realize how they're doing it.
Yeah,
Shor's algorithm is pretty cool.
But the algorithm is really neat and beautiful.
It really is.
Wow, this guy deserves a genius.
I know. And then coming up with the first error correction scheme like a year later. It was quite a productive year for Peter.
Yeah, but he had a track record in this kind of research, because before he discovered or invented this algorithm, he was already very famous expert in number theory.
Okay.
So he published a number of papers on number theory.
Interesting. That's funny because my focus is on quantum computing. I don't know anything about Peter Shor before.
He was already famous in that.
That's interesting. Yeah, that makes sense. You don't seem brilliant. You don't just be that brilliant overnight, right?
Yeah, so that's probably why, he naturally, came up with.
But anyway, returning to your research, let's get back to the material science. Okay, so you had this classical machine learning sort of down select or attempt to predict the properties. You're now looking at quantum machine learning. Replication or enhancement of that potentially.
Yeah.
So then you were talking about from that smaller pool of potential materials is the next step to try to simulate using a quantum computer, the DFT type.
Yeah, we are going to first simulate using DFT, but it's also where we can use quantum computer.
Okay.
Because when you do DFT simulation, you need to have an input. Gas the arrangement of atoms. Right. And then you have many elements we call it supercell. So essentially you can imagine this is a cubic grid, right? And in each grid point you decorate with some element. And there are so many permutations.
Like you said.
Yeah. You have different permutations. You still representing the same composition. Right? We are not going to do all the permutation, right? It's going to be infinite permutations.
Right.
Yeah, that's probably where you can use a quantum simulator to come up with some statistical.
Okay, so the machine learning step, whether it's classical or quantum, narrows down the candidates. The quantum step runs predictions of what that initial decorated state would be, the supercell state.
Yeah,
and then that's the input to the DFT.
Exactly.
I see.
Exactly.
Is there a quantum algorithm that's equivalent to DFT? Is there a QDFT?
Very good question. I saw some papers. So, for example, they applied quantum counterpart of DFT, not necessarily DFT, quantum counterpart. We call it DFT-based molecular dynamic simulations.
Okay.
Yeah.
Interesting.
But that's this kind of very general, natural extension. Right? We know quantum computers, they probably good for solving eigenvalue problem.
Right.
Yeah. And then
if you want to simulate a quantum system, you need a quantum device.
You need to get the eigenvalue. Yeah.
Interesting. And so, is this possible on sort of NISQ machines, or is this something that would need fault tolerant qubits to an error correction to scale?
So in principle, you need
fault tolerant.
Yeah, you need like one of the slides. So this morning.
Right.
Yeah.
That was it was a qubit pharmaceutical.
Yeah. So basically, he's doing similar thing, but he's working on this molecular systems.
Right.
So my interest is mostly in solid systems, which means you can repeat.
Okay, interesting. Because the structure repeats over and over again. I see.
For example, copper, right? It's it's infinite periodic.
Right. Yeah. Interesting.
Yeah.
Cool. So, okay. So, then what's sort of the scale of logical qubits that you would need to do something that has clear advantage over any kind of classical approach, do you think?
So far, I think if I have 7 perfect qubits.
Oh, really? That small a number?
Yeah.
Wow.
So I can include everything.
Right. You were saying.
Any material,
Yeah.
right? As far as they have some composition
Interesting.
in quantum circuit.
Huh. That's really interesting.
Yeah. In the paper we published, we saw some preliminary result. So we input the chemical formula, and if it is implemented in quantum simulator, only the bars representing the element showing up. Only other bars, they don't show up. Right? Each bar here means one string, zeros and ones, and each element.
Right. Okay.
Right. So basically, let's say you have ABC 3 elements.
Yeah.
And then their model ratio is 1 to 1 to 1.
Mm-hmm.
And then you can do this encoding to a quantum circuit, and then you measure it right away. And in the end, you will only see 3 bars. Measure many times. Those 3 bars will have the same amplitudes. Amplitudes.
Yeah.
But because of noise, all the possible zeros and ones, they start to show up.
I see.
Yeah.
I see. So you can simulate 7 perfect qubits. There's no performance advantage on a classical simulator, or we're obviously doing it just a straight classical way, or is there some like algorithm or approach that you're using that has advantage in either classical or a quantum way? Then?
Yeah. So far we are looking at the classical quantum algorithm. By classical quantum algorithm, I mean like Peter Saw or Grover's algorithm.
Yeah.
So we are looking at how can you, let's say you have 3 bars showing up right after many shots.
Right.
How can you change those 3 bars into 1 bar, and then that 1 bar representing some kind of encoding.
Interesting.
Some category.
Okay.
Right. So no matter.
So it's almost a compression method.
Yeah. It's also this quadratic search problem.
Okay. Quadratic search. Yeah.
That has been shown by Grover.
Right. Grover. Yeah.
I think that's where we can possibly see quantum.
And what would like the ideal sort of outcome in your mind? Is it some sort of approach to be able to, efficiently predict the alloy composition that would have the high entropy alloy composition would have certain characteristics that you desire, basically sort of designer materials, if you will? Is that kind of what you're trying to do?
Yeah, exactly. So let's say you train your quantum circuit using available data or good catalysis or bad catalysis or carbon dioxide capture. Right? And then in the end, you will come up with some new composition. Right, kind of like extrapolation. Yeah, I'm very interested in recent classical machine learning algorithm like GPT.
Yeah.
It's generative models.
Right.
Yeah, you can come up with. So you learn the probability distribution of classical data, and then you take 1 point from the probability distribution, and then you based on that point, you can come up with some new thing.
I see, and then you would that would be the input into the quantum circuit. To predict or simulate those characteristics, or the supercell. Yeah,
and there are some recent research on people have published some paper on so-called quantum attention mechanism. Yeah, so essentially, right. So in classical machine learning, each token representing, for example, each English word. Right, so they have some kind of correlation. Right? So, for example, you say a sentence, this word pays attention to more attention to another word. Right. So you can imagine each word is a particle.
Right. Yeah.
Or not necessarily a quantum particle. In that way, you can think it's a classical particle. Right. And you start to have this correlation.
That's interesting. What I really find fascinating is that you're combining sort of cutting edge classical techniques with these emerging quantum techniques. I mean, I feel like that's going to be, when we get to some kind of working quantum advantage for some, material science or chemistry or other scientific physical science application, it is going to end up being some very tightly bound combination of classical and quantum that actually delivers that result, right?
Exactly. Yeah.
Very interesting. Well, that's fantastic. You also mentioned yesterday when we were talking the stuff you're doing with the summer program in Africa. Tell me a little bit about that, because that sounded really fascinating.
Oh yeah, so the whole overall program is called ASESMA. Yeah, A stands for Africa, and so basically this program is trying to collaborate with physicists in Africa to help promote DFT or electronic structure.
Right.
Yeah. So it was originally started by Richard Martin. I think he retired from UIUC. He has a very classic book on electronic structure.
Right. The name is familiar. Yeah.
Actually, you also mentioned the innovative ABS Innovative Fund yesterday.
Yeah.
Actually, he got one of the innovative fund for this electronic structure. Maybe the first. Yeah.
Oh, wow.
Yeah, the first version of this innovative.
Oh, that's great.
Yeah, he
that's
and his
awesome.
collaborator.
So he started this program sort of collaborating with African physicists. And what you've done it now 3 years, I think?
So he has been doing this.
No, but you just started being.
Yeah, I was planning to start before COVID, but because of
COVID,
so I only started.
Sort of slow travel down.
Yeah, I only started last year. In
Okay.
Kigali, Rwanda.
Right.
Yeah,
right.
So,
and what is it you do when you go over there? It's like a couple of weeks, you said, right?
We did 2 weeks.
Yeah.
Yeah. So each teacher taught one module. So some people taught electronic structure. I did a small module about machine learning. Yeah, presenting my research.
Cool. And this year is going to be Nigeria?
Yeah, this year, we're going to be Nigeria. And this year, we call it a mini assessment.
Okay.
Yeah, only maybe 30 people focusing on people from Nigeria. But next year, we are probably going to do a much bigger version I think it's in Ghana.
Oh, cool. Yeah. And this year, you're bringing, your topic is going to be quantum computing or something related to quantum computing?
Yeah, this year I'm planning to teach students some basic.
Excellent.
Yeah.
That's great. That's really great. And what sort of, you said mini is 30 people. What's the sort of normal size then?
Normal size is about double or triple.
Right.
Yeah, double
That's
or
really
triple.
great.
But much more countries students.
I see. So you're bringing people to one location, but they're coming from multiple countries.
Yeah.
Got it.
So at least 10 African or more than 10 African countries.
Great. That's amazing.
Students were involved.
That's really great. Well, fantastic. Thank you so much for joining me. This has been a really good conversation.
Thank you so much, Sebastian.
Thank you.
Okay, that's it for this episode of The New Quantum Era, a podcast by Sebastian Hassinger and Kevin Roney. Our cool theme music was composed and played by Omar Costa Hamido. Production work is done by our wonderful team over at Podfi. If you are at all like us and enjoy this rich, deep, and interesting topic, please subscribe to our podcast on whichever platform you may stream from. And even consider, if you like what you've heard today, reviewing us on iTunes and or mentioning us on your preferred social media platforms. We're just trying to get the word out on this fascinating topic and would really appreciate your help spreading the word and building community. Thank you so much for your time.